Okay, let's have a quick recap of vectors and what's meant by a vector. So a vector is a physical quantity and a physical quantity can be the scalar or it can be a vector. So a scalar quantity has magnitude only, and an example of that is mass. And a vector quantity has magnitude and direction. So an example of a vector quantity is force. When we represent vectors, we represent them as a line, so with an arrowhead. So this would be the vector from A to B, and this on this side is the initial point, and that's the tail, and then the head is called the terminal point. And we write this as A to B with a little arrow on the top. The length of the arrow is the magnitude of the vector, and when we're discussing vectors, so A to B, if we have that arrow or that vector A to B, if we reverse the direction B to A, so A to B equals B to A. OA, if we have a vector OA, this is a position vector, and what that means is we go from an initial point O, so if we draw our X and Y axis, so this is our x-axis, this is our y-axis. So if we go from an initial point O, which is our origin, and we go to a point A, so this is O and that's A, so this A would be our terminal point. So OA is a position vector as shown here. AB, we write AB, this is a shift relative to A. So what we mean by that is, so if we had AB along here, this would be AB, and we consider that as a displacement vector. So if we had a displacement along the x-axis and on the y-axis, this is 3, this is 2. So this is a displacement vector of 3, 2. And this would be equivalent or equal to another vector over here, which goes in the same direction, A, B, and again with a displacement of 3, 2. So in Cartesian form, we write 3, 2. and when we're discussing vectors, x, y becomes I, j. So 3i plus 2j, a to b, is 3i plus 2j. So like, and in column form we write that as 3, 2. Okay, and we have our x and y in here and here. So this would be our I, which is the representative of x. J is our y-axis. Then this vertical axis here we call k, or sometimes we call it z. So in 3 dimensions the axes are labelled I, j and k, and in column form we write it as I, j, k. When we're adding vectors, so vector addition, vectors, we have to remember, have direction as well. So if it was scalar, which no direction, we'd have 5 plus 2 equals 7. With vectors we use, one of the things we use is called the triangle law. And what we do here is, if we have a vector, let's say A, going in this direction, and then another vector going in this direction, we form that into a triangle. We represent these two vectors by the two sides of a triangle. So we'd have this vector here, so we translate, and this vector we translate here, so it forms a continuous vector, so tail to the head. So we're bringing this one across here, like so. So this would be our A, B, C, and the third side of the triangle, which we'll draw in red, is the resultant force. So this would be our resultant force. So we notice in this that the two vectors we're adding together go from the tail tip, and then the tail to the tip, that way round, and our resultant vector, this is anti-clockwise, and our resultant vector is clockwise. The other law we use in vector addition is called the parallelogram law. And in this, if we have two coinitial vectors, so coinitial means they start at the same point. So if we have a vector here, OA or OB, and a vector here, OA, then the diagonal of the parallelogram that we draw it represents the resultant vector. So what we have to do is we have to move this vector, the OB vector, onto tip to tail. So this would become our vector P, and this would become our other side of the parallelogram, and our resultant vector would be in red. So we're going to draw our resultant vector here. So what we have to notice here is that OB is equal to AP, and our OA vector equals BP, and then our resultant vector R. Also, in vector notation, if we write small a, this equals vector OA. So this would be A, and if we write a B, this would be our vector OB. When we look at properties of vector addition is commutative. What do we mean by that? Well, we mean that if we have A plus B, it equals B plus A. And we can prove that. So the proof is, if we draw again the parallelogram from our origin O, and we label this A, C, and then our resultant vector, so we're going to move C across over here, so this would be our point B, and this would be our other side of the parallelogram, and our resultant would be R, which go from the origin up to here. This is R, and this would be A, this would be B, similarly this would be also A, and this would be B. So if we look at our parallelogram, our vector OA equals AC, so OA equals OA plus AC rather equals O to B, which is our resultant. So this means that A plus B equals R, which is our resultant vector. And also, for proving this commutative property, OC, so we have OC, which is B, plus CB, which is A, also equals OB. So this means that B plus A equals R. Therefore, A plus B equals B plus A. Similarly, we can show that vector addition is associative. And what do we mean by that? So here we mean that if we have A plus B plus C, this equals A plus B plus C. And again, we can prove this by drawing our parallelogram. So let's quickly draw that. So here we would have A, B, and here we would have C, and we'd have O. This would be C. So from here we see that O to A plus A to B. So this is O to A plus A to B would be the resultant, which is in red. Let's draw that. And that's R. And we'd also have another resultant in the other way. And that would also be equal to R. So this O to A plus A to B is O to B. So if we write this as A plus B equals OB, which is R. Similarly, if we have triangle OBC, we have the vector OB plus BC equals OC. So that's OB plus BC is same as OC. So that's A plus B, O plus B, OB was A plus B, plus C equals OC. If we have triangle ABC, we have AB vector plus the BC equals AC. So that means that B plus C equals AC. If we have triangle OAC, so we have OA plus AC equals OC. So here we have A plus B plus C equals OC. From 1, which is here, and 2, which is the one we just worked out, our equation 2, this is the proof of the associative property. Here we're going to have a look at our position vector rule. And what this rule says, if we have two position vectors, say A and B from the origin, so this would be A to this point here, and this would be our B, so this is A, sorry, this is OA, and this is OB. So this would be our, by the triangle rule, AB. So we want to find out AB. So we know that OA plus AB equals OB by the triangle rule. So remember what the triangle rule was. We go clockwise this way, so that will be OA, AB, and the resultant would be O to B. Rearranging, we get AB equals OB minus OA. So this gives us our rule. So the rule is, if we want the position vector A to B, we get the position vector of the second one, which is position vector B, and we subtract from that the position vector of A. And that is our rule. So let's put that in a little box. So quite an important rule which we'll come across again and again. So let's have a look at an example of that. So if we had A, B, C and D as the points, and the position vectors are A, B, 2A plus 3B, and A plus 2B. So those are our position vectors, and we want to find out dB. So find dB and also find AC. So we use our rule, and our rule says we get the position vector for dB, get the position vector for B, which is B, and we subtract our position vector for D rather, so it's A, C, D, D is A plus 2B, so it's minus A minus 2B. This gives us B minus A. When we distribute the minus, we get plus 2B. So our vector is then 3B minus A. Similarly for AC, its position vector of C, which is A plus 2B, 2A plus B, 3B. And we subtract from that position vector of A, and we get A plus our 3B. Here we're going to have a look at vector components and vector units. So if we have x and y as the rectangular components, and we draw our triangle, we get that this is x and this is the y vector, and this would be our resultant vector. So we get x plus y equals r, vector r, which is the resultant vector. If we have a look at this in our vector form with our axes as I and j, and this being our vector A, then A is 3I plus 4j. So 3 along the I-axis and 4 along the j-axis. if we have a look here and we want the magnitude of r, and we write this as r, two lines on either side, this is the square root of x squared plus y squared. Here, if we want the magnitude of our a vector, this is the square root of 3 squared plus 4 squared, and this equals 5. Now if we divide this by its magnitude, divide that vector by its magnitude, we get what's called the unit vector, and we write this as a with a little cap on the top, and this would then equal 1/5 3i plus 1/5 4j. So that's our unit vector. In column form, we write this as 1/5 3 4. Okay. If we wanted to write our x and y in this form, so if we had a point here as 2, 3, as a position vector, we would write 2i plus 3j, the little cap on the top. Now if we wanted to find, let's move this up a little bit, if we wanted to find our vector from A to B, so this would be A as 2, 3, and B position 6, 7 as xy, and we wanted to find A to B, our vector. Then what we do is we write it in column form, so this would be as 2i plus our j underneath, which would be 3j, and we subtract our b from the a, so our b should be on the other side, so this would be our 6i 7j. Okay, and subtract the 2, and then 6 minus 2 is 4, and 7 minus 3 is 4. So when we do that, we get the answer 4i plus 4j. If we have a quick practice, so our A vector is 3i plus 4j plus 2k. Our magnitude of A then becomes the square root of 3 squared plus 4 squared plus 2 squared. Our unit vector A with a little cap on the top then becomes 3 over square root of 29, because this works out as square root of 29. So 3 over square root of 29i plus 4 over square root of 29j plus 2 over square root of 29k. And in column form we can write that as 1 over square square root of 29, 3, 4, 2. Okay, if we're given a point A on the line L1 and the position vector of A is -2, 3. So remember, the top is the I and the bottom one is J. And A is on line L1. Now if we take a parallel vector to the line, so it would be in this direction, and we work out the vector is, say it went, because we're going in this direction, if we draw a triangle, it's going to be the rise over the run, which is going to be, say, 2 minus 1. So we take a parallel vector 2 minus 1 to L1. Now this is called the direction vector, and what happens is we can go from OA to any point on L1 by adding multiples of the direction vector. So if we were here on OA, 1 adding the direction vector, so if we're here on A, adding the direction vector once would take us to about here, and twice would take us to about here. So if we label that R1, so R1 equals the position vector minus 2, 3 plus, and we said we're adding the directional vector twice, 2, and that's the direction vector. So this is the position vector and this is the direction vector, and this is a parameter. So this gives us the vector equation of a line, and that says that R is A plus lambda, or sometimes it's mu, B, and that's the vector equation of the line. A is a fixed point. A is a fixed point on the line. Lambda or mu is a parameter, and B is a direction vector parallel to the line. Let's do a quick example. Find the vector equation of a line passing through points A is 1, 5 and 2, and point B is 2, 1 and 3. So we know that A to B we can get the position vector of B minus the position vector of A, which would be 2, 1, 3 minus 1, 5, 2. And this would give us our direction vector, which is 1, 4, 1. Oh, sorry, 1 minus 4. 1 minus 5 minus 4. Okay, and then our vector of the line, or vector equation, would be that, plus the point on the line, which would be either A or B. So we'd choose A on this, so it would be 1, 5, 2, and plus lambda, and then our direction vector. Adding position vectors, if we have the vector A equals x and our unit vector I plus y, so we call this x1, y1, and our unit vector j, and we have B as x2 unit vector I plus y2 unit vector j. Then our A plus B, so we're adding the vectors together. We add the unit I vectors and add unit j vectors. So this would then become x1 plus x2I plus y1 plus y2j. So if we do this in column form, if we have our vectors 9, 7, 5, so this is our I, this is our j, this is our k, and we're adding this to our vectors 2, minus 1, 3, and again this is our I vector, this is our j, and this is our k. Then our resultant vector becomes 11, minus 6, and 8, I, j, k. When we're subtracting the position vectors, so that would be A minus B, we have x1 position vector I minus x2 position vector j plus y1I minus y2j. We can actually move the I outside, so we get x1 minus x2I and then y1 minus y2j. So let's put that in column form. So if we have 9, 7, 5, that would be I, that would be j, that would be k, and we're minus 7, 8, 2, I, j, k. That would be 9 minus 7 is 2, 7 minus 8 is minus 1, and 5 minus 2 is 3. And that again would be I, j, k. Okay, if we go on to multiplying by a scalar, say the scalar quantity was m, so our m A we multiply the scalar by x1 I plus y1 j, and this is nothing but m x1 I plus m y1 j. If we have minus m and we multiply by a, this would be m minus a, and similarly this would equal minus ma. If we have two scalars, m and n, multiplied by a, this would equal m na, and this equals m n. So that's when we multiply by a scalar. An important rule that we have to note when we're multiplying is that any vector squared gives us its magnitude. So for example, if we have a squared, this equals the magnitude of a squared. So for example, if we want to prove, so we'll do this as a little aside, prove that a plus b squared equals the magnitude of a squared plus the magnitude of b squared plus 2a b. So we can say that a plus b squared plus a plus b squared. So that's a plus b squared. This equals a, so we're going to do our FOIL method, a times a plus ab plus ba plus b times b. So we said this was nothing but the magnitude of a squared plus ab plus another ab plus the magnitude of b squared. And this equals a squared plus b squared plus 2ab. Okay, as another important multiplication is the dot product, and we write this as a dot b. Now, a dot product always gives you a scalar quantity, and how we do this is by multiplying across, and we multiply the unit vector I with the unit vector I, and the unit vector k with the k, and the j unit vector with the j. For example, if we had A equals 2i plus 3j plus 5k, and our B equals 5i plus j plus 2k, and we need to find our dot product A, B. This is also known as the scalar product. So how we do this is we write it in column form. So we'd write 2, 3, and then our I would just be 1, dotted with our 5, sorry, this should be a 5 because we're doing the A, dotted with our 5, our J is just 1, and our K is 2. So now we do our multiplication. 2 times 5 is 10, 3 times 1 is 3, and our 5 times 2 is 10. Now we add these two together, these three together rather. Now we add these three together, and this equals 23. And that is our scalar product. The i's, when we multiply with an I, disappear, and this is why we're left with a scalar product. Basically what's happening is we have, when we multiply A dot B, so this is as a little aside, we're doing A, B, cos theta. Our cos theta, when we multiply the I with the I, equals 1, and then the I disappears, leaving us with a scalar product. Similarly, k times k cos theta is 1, and j times j cos theta is 1, and they disappear, leaving us with a scalar product. Dot product, this is multiplying the two vectors A and B, and called the dot product because of this sign that we used for the multiplication. Now the dot product equals the magnitude of A multiplied by the magnitude of B cos theta, and this is a rule we have to remember. When we are drawing these vectors to see what's going on, so if we draw a vector A in this direction and a vector B, say in this direction, so this would be our vector A, this would be our vector B, then the magnitude of A is the length from this point to this point, and the magnitude of B, which we represent like that, is from this point to this point. The angle theta is the angle where the two lines meet and the vectors go away. They both go away from that angle. So the arrows are quite important in working out which angle we're discussing. Now the dot product is also called the scalar product. because it has no direction, and also sometimes called the projection product. We discussed why it was called the scalar product before. It's called the projection product because to multiply two vectors, they have to be in the same direction. And we do this by taking the cos of theta. So if we have our vector A, so let's draw that here, and our vector B, say over here. So to get A, B, we have to use this here as A cos theta up to this point here where A is projected onto B. This is our B, and therefore A, B. So our AB equals the magnitude of A multiplied by the magnitude of B cos theta. And similarly it can be A cos theta multiplied by the magnitude of B. If we have two vectors at right angles, so we have our vector A here and our vector B here. The dot product is sometimes said to represent what's called parallelism. So when the vectors are at right angles, i.e. perpendicular, then the dot product is 0, and this is another important fact. So our dot product is 0. Okay. And why that is, it's because when we have A, B equals magnitude of A, magnitude of B, cos theta, when it's at 90 degrees, our cos theta is 0, so this becomes magnitude of A, magnitude of B times sine 0, that's cos theta, which will equal 0. Another important rule that we have to remember when we're using vectors is cos theta equals, and we have the dot product of A, the direction vectors A and B, divided by the magnitude of A multiplied by B. So let's use that as an example. So if we have the direction vector of A equals 2I plus 3J plus 5K, and the direction vector of B equals 5I plus J plus 2K. Okay, we previously worked out that our dot product A B was 23. Now our magnitudes, remember the rule, it's from Pythagoras to work out the length of the vector. So our magnitude of A is the square root, so let's just do a quick square root, of 2 squared plus 3 squared plus 5 squared, and this is square root of 32. The square root of and this is the square root of 38. And then the magnitude of B, we have the square root of 5 squared plus 1 squared is J plus 2 squared, and this is the square root of 30. So our cos theta then becomes our dot product 23 divided by square root of 38 multiplied by the square root of 30. So then our theta is the inverse cos square root of 23 over the square root of 38 multiplied by the square root of 30. The cross product is also used when we multiply two vectors. So in the cross product we write A multiplied by B, and this gives us another vector. And this vector is at right angles to both A and B. So here I've tried to represent this, not done a good job, but so here we have a plane containing A and B, and then this would be the vector A multiplied by B, the cross product of AB, and it's at 90 degrees to both A and to B, and the plane that A and B is in. So this is in 3D, in 3 dimensions, and we can calculate this vector A multiplied by B, and this equals the magnitude of A multiplied by the magnitude of B sine theta n. So let's just go through this. So theta is the acute angle, or the angle between A and B. Our A is magnitude of A, or the length of A. And our B is the magnitude of B, or the length of B. Our n is a unit vector, and this is at right angles to A and B. The cross product has both magnitude and direction. if we're discussing two unit vectors, so two unit vectors, and they're if we're discussing two unit vectors and they're perpendicular, then the cross product will be 1. The cross product is said to represent perpendicularity, just as we said the dot product was said to represent parallelism. So if these two unit vectors were parallel, then the cross product would equal 0. Let's have a discussion about magnitude and direction. So when we're talking about polar coordinates here and comparing it to our Cartesian coordinates over here, so this is polar coordinates and this is Cartesian. Okay, we have a vector A in both cases, and our angle theta. Polar coordinates, this would be, say, x and the y. So our x equals, so this would be r and theta. So our x equals r cos theta, and our y equals r sine theta. Here we'd have our x again here and our y here, and this would represent r. So our r is square root of x squared plus y squared, and our theta is inverse tan y over x. Generally speaking, the magnitude of the cross product is equal to the area of a parallelogram. With the vectors A and B for the sides. The volume of a parallelogram actually, when it's a volume, it's called a parallelepiped. So let's say that P, parallelepiped, having A, B, C as sides, is calculated by A, and then B times C, which is B C times A. So the volume equals, usually written by A, and then the cross product of B times C. Go over the easiest method to remember when doing the cross product. The cross product is the determinant of a 3 by 3 matrix. So let's just have a quick go at finding the determinant of a 2 by 2. So if we had 4, 7, minus 2, 4, this would be going this way, 4 multiplied by 4, and then we minus 7 multiplied by minus 2. So this would be 16 minus 7 multiplied by minus 2 is minus 14, and this equals 30. So we're going to apply that into a 3 by 3 matrix. Now the first thing we have to do when we're doing a 3 by 3 matrix is we make x1 positive, we make y1 negative, and we make z2 positive. And then we do our determinant calculation using that. So this one becomes positive, negative, positive. Then for our first calculation, we draw a line through x1 and down. Now we do our calculation, so this would be x1 multiplied by the determinant of these four here, which would be y2, z2, y3, z3. Okay? Then our second one, we draw a line down and across, and we use x2, z2s, x3 and z3 as our 2 by 2 matrix. So this then, don't forget the negative, so this becomes negative y1, and then we get the determinant of x2, z2, x3, z3. And then finally we get through z1 a line and across, and this becomes our 2 by 2 matrix here, so this would be z1, and our 2 by 2 matrix would then become x2, y2, x3 and y3. Okay, let's have a little practice. So if we had our matrix as 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is going to be our example matrix. First of all, make this positive, negative and positive. So this then becomes x1, and we're going to do our calculation based on here, so it would be y2, z2, 3 minus z2y3, then minus our y1, x2 going across z3 minus, going this way z2 x3, then plus, I'll just go down here, z1, then this would be our x2 y3 minus y2 x3. So now we just plug in our numbers. So for our example matrix, this would be 1 as our x1, 5 multiplied by 9 minus 6 multiplied by 8, minus 2, 4 multiplied by 9 minus 6 multiplied by 7, plus 3, 4 multiplied by 8 minus 5 multiplied by 7. And this, when we calculate it, our determinant is 0. Have a little practice with working out a cross product. So if we had the vector r, direction vector, equals 3i minus 2j plus 4k, and we had the direction vector s equals minus 4i plus 3j minus 2k. So we want to find the determinant or the cross product. So first of all, we make a 3 by 3 matrix. So we have our I, and we have our j, we have our k. Then we put our 3 there, minus 2, 4. Then minus 4, 3, and then minus 2 to give our 3 by 3 matrix. Remember to make this I positive, the j negative, and the k positive. Now this then, when we use our rule that we discussed before, becomes I minus 2, 4, 3, minus 2, then our minus j, then our 2 by 2 matrix becomes 3, the minus 2 over here, minus 4, and then our 4 on the top, and then plus our k, and our 2 by 2 matrix becomes 3 minus 2 minus 4, 3. And then when we work that out, that becomes I multiplied minus 2 times minus 2 minus 4 times 3 minus j, 3 times minus 2 minus 4 times minus 4 plus k, and then this will be 3 times 3 minus 2 times minus 4. When we work that out, this is minus 8i minus 10j, so that should be just minus 10j. I don't know where that one came from. And plus, this becomes k. So our r cross product with s is minus 8i minus 10j j plus k. And remember, the cross product has magnitude and direction. Okay, we're going to discuss two methods of finding the magnitude of a cross product. So in the first, what we do is we make our 3 by 3 matrix. So we have our I, j, k, and then 4 minus 3, 6, and then 1, 4, minus 4. Remember to make this positive, negative, positive. And then we work out the determinant. And that equals minus 12i plus 22j plus 19k. Then our cross product, the magnitude of our cross product, A times cross product with B, the magnitude will equal the square root. So let's just do a quick square root sign of 12 squared plus 22 squared plus 19 squared. This is the square root of 989, and that's approximately 31.45. So that's one method. The alternative is to use our A times B. The magnitude is AB sine theta. So here we get our magnitude of A equals the square root of 4 squared plus 3 squared plus 6 squared, and our magnitude of B equals 1 squared, which is I, plus 4 squared plus 4 squared. This equals the square root of 61.78, and this one the square root of 33.57. Now cos theta we know equals AB, the dot product over A, the magnitude. So this is minus 32 over square root of 61 square root of 33, and that is 0.713. So our theta then equals 135.5 degrees. And using that we get our A cross product B, the magnitude equals square root of 61 multiplied by square root of 33 sine 135.5 and that again equals 31.45. In this example, we're asked to find the value of p for which the direction vectors a and b are firstly perpendicular and then parallel. So for a and b to be perpendicular, that's a perpendicular to b, then our dot product, which is a dot b, has to equal 0. So if we draw this in column form, so we have 3, 2, 9 dotted with 1, p, 3, and that should equal 0. So when we do the dot product, we get 3 times 1 is 3 plus 2p plus 9 times 3 is 27 equals 0. So 27 plus 3 is 30 plus 2p equals 0. There are p equals minus 15. In our second case, when we want to find p when they're parallel, so for a and to be parallel, a has to equal some parameter multiplied by b. Then we get this a 1i plus a 2j plus a 3k, and here we'll have b 1i plus b 2j plus b 3k. Okay, so a1 over b1 equals a2 over b2 equals a3 over b3. So in this case we have our first is 3 and our I was 1 equals, then the next one is 2 over p equals 9 over 3. So this equals 2 over p, and our p then equals 2 over 3. The test for consistency shows whether two lines in 3 dimensions actually intersect or are skew. So how do we do this? First of all, we equate the two. So we equate the x's and the y's and then the z's. So for the x we have 2 plus s equals minus 1 minus 2t. For the y we have minus s equals t, and for the z we have z minus s equals 2 plus 3t. And now when we label that equation 1, 2 and 3, And now we have to find the S and T parameters and see if they're consistent. So if we sub 2 into 1, so sub 2 into that equation, we get minus t plus 2t equals minus 3. Our t equals minus 3. So that's our t. Now if we sub that into 2, we get s equals minus 3. So our s equals 3. Now to check if they're consistent, we sub this into our third equation for z, and we get s equals minus 3 minus 3, and this is not the case, so s does not equal minus 3. That is minus 3. So the lines are not consistent. So the lines are skew and do not intersect. So what do we mean by the lines are skew? Well, we have this line L1 and we have this line L2. So they do pass over each other, but in space, if we look at it in 3D, at a certain angle, this L1 will be like this, and the L2 will be like this. But when we look at it from this direction, they will be crossing over, but with a distance between them. Here we're asked to find the shortest distance between a point and a line. So if we draw a quick diagram, this is our line L, which is here, L, and our point A, which is here, and then the shortest distance between the point A to the line L is a line perpendicular to the line that we want, and what we're after is our A to P, the point P being here, perpendicular on the line from the point A, and the distance we're interested in is small d. We've also got a direction vector A in this direction parallel to the line, and a direction vector B parallel to the line that we're interested in finding. First of all, let's write this line equation in column form. Now this represents the position, this represents a direction vector. So our direction vector for A, we already know, is 3, or little a is 3, 1, 1, so we can write that here. And for this first method, we're going to use the scalar product. And the scalar product says when we dot A with B, we get the magnitude of A multiplied by the magnitude of B cos theta. And The other thing we need to know is that this line is perpendicular. The shortest distance is perpendicular to the line. So in that case, theta equals pi over 2, and cos theta would have to equal 0. So when cos theta is 0, this disappears and we're simply left with a dot b equals 0. So a dot b equals 0, we know a is 3, 1, 1 as a column vector. We need to find b. So how do we do that? Well, we know that this line that we're interested in is a to p, that vector, which is also little d, what we're interested in. And we know that this is the vector position of p minus the vector position of a. We know the vector position of a is minus 6, 1, 21. We need to find the vector position of p. So how do we do that? Well, we know that in some way p lies on the line with this equation. So if we write 3t minus 4, t minus 5 and t minus 1, the vector position of p has to satisfy this equation for some value of t. So we can use that unknown and then minus the vector position of a, which is minus 6, 1, 21. And this would give us, when we work it out, 3t plus 2, t minus 6, t minus 22. Okay, now let's take a step back and see what we've got. First of all, we've got here the vector position for p. We've got here the vector position for a. And here we've worked out a to p, which equals d. And this is also the direction vector for b. Okay, so now we can do our a multiplied by b. So a multiplied by b equals 0. So our b is 3t plus 2, t minus 6 and t minus 22. So we know that the direction vector for b has to satisfy this equation for some value of t. So this would be b. Let's just write that down so we don't get confused. And then we're going to multiply this by our direction vector for a, which is 3, 1, 1. So our dot product then is going to have to equal 0 because they're perpendicular to each other. So when we work out the dot product, we get 3t plus 2, t minus 6 plus t minus 22 equals 0. 11t, when we get all our t's together, minus 22 equals 0, therefore t equals 2. Now, a lot of people make a mistake of where do we substitute the 2? Well, we want b, d, so we have to substitute it into this equation here. Substitute our t's into here and we get our little b, we get our ap, we get our d. So let's do that. So 3t, so that's 6 plus 2 is 8. So we're going to sub t into AP or B, and we got 8 minus 4 minus 2, and if we take 4 on the outside we're left with 2 minus 1 minus 5. So our magnitude of AP, which is our length or the shortest distance, the magnitude equals 4 square root 4 plus 1 plus 25, and that's 4 square root of 30, and that's our answer. Now the other thing we can be asked is to find the point P. So we know the vector position P, which is here, so which is what we're interested in here. This equation represents the vector position of P for some value of t. Now we've got t equals 2. So if we sub t equals 2 into this equation, then we get the vector position of P. Here we're going to do the same question, but we're going to use the vector product. To find the distance, the shortest distance between a point and a line. If we draw a quick diagram again, this point A can be here or here in 3 dimensions, and then we draw a parallelogram from the point A to a point P, a line, sorry, from the point A to the point P, and then make a parallelogram. The point P can be any point, but we're already given a point with minus 4 minus 5 minus 1 as a point, so we're going to use that as P. So the vector product area of a parallelogram the area equals A to P, and we want the magnitude of that multiplied, that's the vector product. A is the magnitude of AP multiplied by u being the direction vector, so our magnitude would be one side of the parallelogram and AP would be the other side. Also, A equals the magnitude of u, which we discussed is one side of the parallelogram, multiplied by D, which is the height of the parallelogram. So when we want to work out the distance, the little d, which is the height of the parallelogram, we get D equals AP vector product with u, and divide that by the magnitude of u. Okay, so let's do this for this question. Let's use this equation now. So we have AP, that's what we want to work out first. So we know that's the vector position of P, which we're using as minus 4 minus 5 minus 1. Subtract the vector position of A, which is minus 6, 121, and we get minus 2, 6, 22. And our U we're already given, and that's 311. So now we have our AP cross product with U, and we draw our matrices I, J, K, minus 2, 6, 22, 3, 1, 1. So we get I 6 minus 22 minus J minus 2 minus 66 plus k minus 2 minus 6 times 3 is 18, minus 18. So this equals 16 minus 16i plus 68j minus 20k. And then when we simplify that to multiples, we get 4 minus 4, 17 and minus 5. So our d equals 4 square root of 16 plus 2, 8, 4 plus 25 divided by the magnitude of u, which is square root of 9 plus 1 plus 1, and that's 4 square root of 30. Just as an aside, if we want the volume of a parallelepiped, so the volume, if we're given the vectors for the sides as A, B and C, in 3D this would look like our Z along here, our X and our Y. So our parallelogram would lie along here, here, say there, and this would be our A, this would be our B, and this would be our C. So the parallelogram would lie across here. Like so. So this should be a little bit more tilted to this side. And then our area would be given by C multiplied by B, this being C. So this would be this face that we're looking at. So that's the area of one face. A equals C times B. So that would be a vector product. And then our volume equals the magnitude of A dot product with B times C.